Hello and welcome to a video tutorial for the 2009 Electricity and Electromagnetism exam. Question 1. Sean is in the physics lab using a mass spectrometer to measure the mass of an unknown atom. In the mass spectrometer, an electron is removed from an atom producing a positive ion. The positive ion is then accelerated by a constant electric field between two metal plates. A positive ion is created 1 centimeter above the bottom plate, and it accelerates towards the top plate, and the ion has a charge of 1.6 times 10 to the negative 19 coulombs. And what we have to do is draw an arrow showing the direction of the electric field between the plates. So first we need to work out which plate is positive and which is negative, and if we have a positive ion accelerating towards this top plate, then it's being attracted by the top plate, and if this is positive, then that means the top plate has to be negative, right? Because negatives attract positives. If it was positive, then obviously they would be repelling each other, or the plate would be repelling the ion. So that means this is positive, this bottom plate. And we need to draw an arrow showing the electric field, so the arrow is going to go from the positive plate to the negative plate. They already have an arrow here, so I guess you can either draw it off to the side or draw it like this. It's a bit strange because they already have the arrow there showing the acceleration of the ion, but that's exactly how the electric field works in this case. The current between the plates is 3.5 times 10 to the negative 6 amperes. How many positive ions reach the top plate in 1 minute? So if we look at the formula sheet here, we've got I, the current, is equal to the charge over time. So let's write that down. Is equal to Q over T. And it's telling us that the current is 3.5. It gives that to us here. And we don't know the charge exactly, because we need to find out how many positive ions it is, but we know that this is equal to the charge over 60 seconds. And we know the charge of a single ion, so what we can do is rewrite this as 3.5 times 10 to the negative 6 is equal to n times the number of positive ions times 1.6 times 10 to the negative 19, all over 60. I'm running out of space here a bit, but I can continue over here. So if we rearrange this, we can multiply both sides by 60 to get rid of this, and then we can divide by this, or we can just divide by this in one go. But we'll end up with this, so it'll be 3.5 times 10 to the negative 6 and we just need to put this into our calculator here. Times 10 to the negative 6, and all of that divided by 1.6, and you have to remember to put brackets in, because if you just put if you didn't have brackets there and did divided by 1.6 times 10 to the negative 19, then it would divide just by 1.6 and times the rest by that, which isn't what we want. So you have to have brackets. So that gives us if we use the right number of significant figures, which is 1, that gives us 1.3 times 10 to the 15th positive ions. Right. Explain what happens. Oops, I don't know if you can see. Explain what happens to the size of the electric force on the positive ion as it moves towards the top plate. So if we have a look at our formula sheet here, what we're saying is that we need to find the changes in the electric force, so that's this one here, as the ion is approaching the top plate. So it's moving, it has velocity, and its distance from the two plates is changing, but that doesn't actually affect this at all. The charge obviously is stable, and we have here E is equal to voltage over distance, but that's between the two plates, so that doesn't actually change when the positive ion is moving around. The electric field strength isn't going to change just because the ion is moving a little bit. So the force isn't actually going to change, the force felt on the ion, just because it's moving, because velocity and distance don't change that at all. So the size of the electric force acting on the positive ion will not change. Will not change as it moves towards the top plate. And we can add in a formula just to make it a little neater. No velocity, basically, that shows. Or velocity isn't involved. I don't know if you can see what I'm writing. I need to get better with this. So D, explain what happens to the maximum velocity of the positive ion if the power supply voltage is increased. Now, as we saw before, E is equal to V over D. And in this case, if we're increasing the voltage, then that means the field strength of the electric field is going to increase, and that makes sense as well. And so in that case, if E increases, I think it's probably better to show it here. So essentially we're increasing the voltage, so that means that if this side goes up, then this side has to go up as well. And in this case it's the change in the electric field strength, because the charge isn't going to change at all. That's going to remain the same. That isn't changed by the voltage, but the electric field strength will be changed. And if we move to the side here, we see that the change in electric potential energy is equal to E times Q times D, and obviously here E is increasing, so that means the electric potential energy has to increase. And that means that obviously all types of energy can be calculated with the same kind of things. So if the electric potential energy goes up, then that means the kinetic energy is going to go up as well. And that's equal to half times mv squared. And the mass isn't going to change, so if this is going up, then that means the velocity squared has to go up, so the velocity has to increase. So explain what happens to the maximum velocity of the positive ion if the power supply voltage is increased. So I think we can just say, so the electric field strength will increase causing electric potential energy to increase. Which causes kinetic energy to increase. And a lot of this is hypothetical, it isn't actually all happening. Obviously the potential energy and kinetic energy will kind of vary a bit, because once never mind, I'm probably just confusing you, causes kinetic energy to increase. The increase in kinetic energy. Will cause the maximum velocity to increase. I hope that wasn't too confusing. The electric force on the ion is 3.2 times 10 to the negative 15 newtons, and we need to calculate the strength of the electric field between the plates. So, the electric force, so that's this here, is equal to 3.2 times 10 to the negative 15, and we have the charge, so we just need to rearrange this a little bit. So F is equal to EQ, and we need to find what the electric field is, the strength of the electric field. So F divided by Q is equal to E, and now we just need to substitute in. So 3.2 negative 15, and this is all going to be over the charge, which we know from earlier is 1.6 times 10 to the negative 19, which is equal to 3.2 times 10 to the negative 15 divided by 1.6. Okay, so that gives us exactly 20,000, which we can write as 2 times 10 to the, 2 times 10 to the 4th. 2.0 is probably better, so I'll just write this here. Right number of significant figures times 10 to the 4th. And the units for this is going to be Newton coulombs, I think. I might be wrong here. I think it's like that. I'm not too sure. Anyway, they're not asking for units, so that's not a big deal. If you just write this, then that'll be correct. Show that the maximum velocity of the positive ion, if it moves from the position shown to the top plate, is this. And they give us the mass as well. So what we have to do here is we've got to find the velocity, so this is probably going to be involving kinetic energy like I showed before. So if we work out EP is equal to EK, so if we can find out EP, then we can find out what the velocity is, especially if we have the mass, because that's what we need to find. So EP, and I'll just remind you again, is equal to E times Q times D. And if we have a look here again, I think the distance, so the distance between them, this is 5 centimeters, and the positive ion is already 1 centimeter forward, so this is going to be a 4 centimeter distance from the positive ion to the top plate. So that's what we'll be using. And we know that the electric field strength is this, so we can write that all in. Oops, keep doing that. Times 0.04, so that's 4 centimeters, times, and the charge is going to be the same, again, 1.6 times 10 to the negative 19. So if we put all of this in, and this is just 20,000, times 0.04 times 1.6 times 10 to the negative 19. 1.28 times 10 to the negative 16. So this is also equal to kinetic, so that's EP, which we can say is also equal to EK. And EK is equal to half mass times velocity squared. So now we can say that, and we have the mass here. What is it? I'll do it over here. 1.28 times 10 to the negative 16 is equal to 5.31 times 10 to the negative 26 times velocity squared. So if we do that down, so we just need to divide both sides by this now, so then we'll end up with velocity squared is equal to this over this. So oops, that's not 16, that's just 6. Or is it 16? Yes, that's 16. There's a mistake there. .31 times 10 to the negative 26 is equal to V, and this is V squared, so I'll just keep it at that, and then I'll take the square root afterwards. 1.28 times 10 to the negative 16 divided by 5.31 times 10 to the negative 26. And that's an awfully big number. But if we're taking the square root afterwards, this is probably going to be right. So if we take the square root of that, so that gives us a fairly reasonable answer here. So this means that V is equal to, you just need to take the square root after you do this to get where I'm up to, is equal to, I'll write the full thing out, 7.3, we won't need the rest because we'll be rounding so much, but so we can say that this is equal to 4. Oh, I seem to have made a mistake somewhere because they give us the velocity here. 1.2. I think. Oh, right. I see what I've done. I forgot the half here on half times mass times velocity squared. Okay, so this here is supposed to be 2. Okay, that makes it that makes it a bit better. 2 times 1.28 times 10 to the negative 16 divided by 5.31 times 10 to the negative 26. Okay, that's very big as well, and we take the square root, and that gives us the 6.9 that we need to get this. So now we can say that velocity is equal to the square root of 2 times 5.31. Oops. Square root of the whole thing. And then this, rub some of this out. Which is equal to 6.9 times 10 to the 4th, as we can see here. Which is what they're asking for. And that is in meters per second. Hopefully that was somewhat useful, and I believe that's the end of question 1, and I'll continue on with question 2 in the next video. See you soon.